The mass of an object is a measure of its total relativistic energy, as evidenced by, or expressed in Einstein's famous equation, E equals gamma mc squared. For an object at rest, gamma equals 1 and mc squared is the rest energy of the object. But more generally, the energy depends on the velocity and thus its value depends on the frame in which it's measured. Now, relativistic mass energy and momentum are both conserved in any collision. So let's use this idea in the following problem. The K0 meson is an uncharged particle that decays into two charged pions according to K0 to pi plus pi minus. The pions have opposite charges but the same mass, m pi equals 140 MeV per c squared. Suppose that a K0 meson at rest decays into two pions in a detector in which a magnetic field of B equals 2 Tesla is present. If the radius of curvature of the pions is 34.4 centimeters, find A, the momenta and speeds of the pions, and B, the mass of the K0 meson. We can solve this problem by relativistic energy and momentum conservation, working in the rest frame of the K0 meson. So, since the initial momentum of the K0 meson is 0, conservation of momentum says that the momenta of the final state pions is equal in magnitude and opposite in direction. So we're going to write that magnitude as p pi. And we can figure out what this momentum is by figuring out the momentum of a charged particle in a magnetic field, since that's the scenario that we have here. Relativistically, we have that F equals dp dt, where p, the momentum, is the relativistic momentum. So d by dt, the force on a particle in a charged particle in a magnetic field, of gamma m v, the relativistic momentum. And this force is, for a charged particle of charge q, qv cross b. Now, since the force of the magnetic field on the charged particle is perpendicular to its velocity, it does no work on the particle. And so the velocity has a constant magnitude. The speed is a constant. It doesn't depend on time. Of course, its direction is changing since these particles are moving in a circle. But because gamma only depends on the magnitude of the velocity, and that's constant, that pulls out of the derivative here. And the magnitude of the left-hand side of this equation is just gamma m times a, the magnitude of the acceleration, the magnitude of d v dt. And then the magnitude of the right-hand side of this equation is just qvb. Now, a, the acceleration, is just the centripetal acceleration of a particle moving in a circle, which is v squared over r. So plugging in v squared over r, we can solve by rearranging for the momentum of this charged particle in a magnetic field, gamma mv, this is the magnitude, and this turns out to be qbr. So we know that the charge of the pions is plus or minus e, and we're given b and r. So we can just plug in those numbers to this equation, and what we'd find is that the magnitude of the momentum of the pions, p pi, is just 206 MeV per c squared. Good. So next we want to solve for the speed of the pions. Since they have the same momentum, the same mass, this speed, so p pi equals gamma m pi u. So we'll call the speed of the pions u. It's the same speed because of, again, momentum conservation. And so the appropriate gamma factor here, gamma u, is just a function of the speed u. And so already we've solved for p pi, we know m pi, and so this relation, the relativistic momentum of the pions, allows us to solve for the speed u. And so that's just a bit of algebra. I'll write it over here, what you'll find at the end of the day. And so see the attached PDF for more details. But what you'll find is that u equals p pi c over root p pi squared plus m pi squared c squared. And plugging in the numbers, we'd find that this is 0.827 c. So they're very fast. So now that we've determined the speed of the pions, we can figure out the mass of the initial K0 meson by energy conservation. So the initial energy in the system Ek is just mkc squared. Since it's at rest, the gamma factor is 1. And this is equal to the final energy, which is the energy of the two final state pions. They have the same energy since they have the same speed and the same mass. So this is 2 times E pi, where E pi is gamma u, which we wrote down here, m pi c squared. So finally, plugging this in here, we can rearrange these equations to solve for mk. Plugging in the numbers, which again, see the attached PDF for details, we'd find that mk is 498 MeV per c squared. Let's review what just happened. By having this decay process take place in a magnetic field, and knowing the masses of the final state particles, the two pions, we were able to reconstruct the mass of the initial state particle. In fact, by doing this, by reconstructing decay products in this way, physicists are able to very precisely measure the masses of particles and even discover new particles. This photo shows an event taken by the CMS detector at CERN in 2012 that shows the characteristics of a Higgs decay to 2 photons. By reconstructing decay products like this one, physicists discovered the Higgs boson in 2012.